Yeehaw! Welcome to a cheeky recap on mathematical induction. The link will be here once I've uploaded this. Mathematical induction was a method of proof, and it was hinged on two key steps. The first step is the base step, sometimes called the basis step. And for the basis step, we just needed to prove, or we need to prove, that the statement works for the initial value, for the lowest value. Typically this is n equals 1. Sometimes it could be more than this. I'll show you what to look for if it is. The question will always tell you what your starting value is going to be here. The second step in mathematical induction is called the inductive step. The inductive step has two parts. In the first part, we are going to assume that our statement is true when n is equal to any other integer k, and once we've made that assumption, then we're ready to prove that it's true for the next number in the sequence n equals k plus 1. Mathematical induction hinges on substituting something from our assumption step into our proof step here. So it's imperative that you always make this assumption. Let's jump into some examples here. There's two things that we need to work with. One is sums, and that's what we're going to start first. So we're going to prove that the sum from r equals 1 all the way up to some integer n of this particular cheeky little mischief is equal to n on n plus 1, where n is greater than or equal to 1. So the question will always tell us what our starting point is. It'll always tell us. Alright, so for this proof, I'm always going to do my base step first. So I need to prove that it works for n equals 1. So I'm going to check. Okay, so my sum, I'm going to start with my first term, which is when r equals 1. Now I would add that to subsequent terms, but there are no subsequent terms because it's my first term. And I'm showing that that is equal to the right hand side. So does 1 on 2 equal 1 on 2? Yes it does. Cool. I'm ready to move on. You must check this step first. It's always worth a mark. A good trick question could be that the base step doesn't work, in which case you'd finish straight away. Now I'm ready for my inductive step. If you're a bit unsure about what this sort of sum notation looks like here and why I only stopped at this first term, this inductive step is going to make it really clear around what's actually going on. So the first thing I'm going to do is I'm going to assume that n equals k is true. That means that I'm assuming that the sum, still from r equals 1, but this time anywhere that I see n in my sum, I'm going to write k. You'll notice that the r's still remain on my left hand side. You'll notice that anything other than k still remains. Sorry, anything other than n still remains. This is a really important point. This is something that appears time and time again during past external exams. Only n is substituted. So if the expression includes anything other than n, if it includes an r, if it includes a j, if it includes a b, whatever it is, you do not substitute that. Only n is substituted. Now that I've made this assumption, I'm ready to prove that n equals k plus 1 is true. So I'm going to prove that the sum from r equals 1 all the way up to now k plus 1 of, again, r's don't go anywhere. I'm only substituting k plus 1 where I see an n. That's going to look like n on n plus 1. So anywhere I see an n, I'm going to write a k plus 1. And this denominator has an n plus 1. So I'm going to write a k plus 1 plus 1. Because that's my n. Alright. Now that we're here, it's probably time for me to unpack exactly what this sum notation here is saying. What this left-hand side is saying is start with r equals 1 and work your way up, adding this expression together, substituting values until you get to k plus 1. So my first value would be when r equals 1. It would be my first term. My second value would be when r equals 2. My third value, and so on, all the way up to when my value is k plus 1. And it's saying that that has got to be equal to, or that is equal to k plus 1 on, and I'm going to write my denominator simpler now, k plus 2. So this is what this sum notation is really saying. Now, the key to induction is to somehow substitute something from our assumptive step here into this section here. The easiest way to do that in a sum problem is to think about what the term before k plus 1 is going to be. The term before k plus 1 is going to be k. So I can actually write my sum as 1 all the way up to k times k plus 1 plus my k plus 1 term. This might not seem super helpful, but what I've just written down here is equivalent to
it's not great.
That's funny. This term here is equivalent to all of this sum right here. And all of that sum right there is equivalent to k on k plus 1. So this is really nice because all of a sudden I can substitute this entire sum out for that thing in my assumption, which is k on k plus 1. Nothing else is going to go away yet. Now that I've made this assumption, I'm just going to use some algebra to make the two sides equal each other. So I'll note that I've got this term here in the middle with its k plus 1 and k plus 2 as a denominator. This one only has a k plus 2 and this one only has a k plus 1. So I'm going to fix that by multiplying top and bottom by k plus 2 and multiplying top and bottom by k plus 1. That way I can add all my fractions together. So that's going to look like this. Now I don't care about the fact that all my denominators are the same. I can get rid of that. I'm going to distribute all of this now. So my left hand side looks like k squared plus k plus 1. Oh, sorry, I did a silly This is a k plus 2. So that means it's going to look like k squared plus 2k plus 1. And my right hand side is going to be equal to k squared plus k plus 1. And I'm done. Now we always finish this with QED, but oftentimes it looks like the external exam is looking for a statement. And my statement is simply to say that that original proposition, that the sum of this gobbledygook is equal to n plus 1, n on n plus 1 is true for all n that are greater than or equal to 1. Nice. Now we're going to look at an example for divisibility. So we could prove sums or we could prove divisibility. Divisibility looks slightly different. We're going to prove that 7n take 1 I'm actually going to put this in a different video.